may be one of the most well-known bits of the Hitchhiker Guides to the Galaxy. In this part, an alien race asks to the most powerful supercomputer the ultimate question. And after 7.5 million years, the computer comes back with the answer 42, which the alien race cannot make any sense of. I chose to start with this clip since to me, and maybe to some of you, this feels like a quite familiar experience. One may have used a significant amount of computer time on a powerful supercomputer, running a sophisticated code that in principle implements a very accurate approach, and yet, when the calculations finished, its output did not make any sense. How can we avoid random results, outputs we cannot make any sense of, and wasting computer time when using Yambo? Shortly, how can we make the most out of Yambo? In this lecture, we will try to answer this very question. First, we need to realize that running Yambo is not an easy task. Yambo is not a black box, and there are several layers of complexity between the question and the answer. The first layer is the phenomenon one wants to study or the experiment one wants to reproduce. For example, photo emission or optical absorption. And then on which material. For example, in which phase is the material, are there defects? Second layer is the theory. That is how the phenomenon is modeled. Here one gets a jungle of acronyms: IPA, RPA, BAC, TDFT, GW. Behind each of these there are approximations, assumptions, and mathematical expressions. The third layer is the numerical implementation of these methods into Yambo. Here one gets into basis set expansions, truncation of sums, discretization of continuum, tricks to speed up calculations such as termination, double grids, etc., etc. Finally, all the technicalities required to run the simulation. This is just the fourth and final layer of complexity when running Yambo. Looking at an input of Yambo can be disheartening. There are so many keywords and so many acronyms. These keywords are connected to the other layers mentioned before. There are keywords to set in the appropriate parameters for the numerical methods, keywords for selecting among the available theoretical approaches and approximations, and even keywords to choose how to parallelize the processes and how to distribute the information among the cores when you're running a parallel calculation. In summary, when we are confronted with a phenomenon or an experiment for which we want to predict or reproduce the outcome, first we need to understand what the phenomenon is, what quantity is exactly measured in the experiment, and we aim to reproduce in our simulation. Second, we need to study the levels of theory that can be used to obtain such quantity, which assumptions and approximation are made in each approach. Third, within the level of theory, how in practice such quantity is calculated. What equations are solved specifically during the simulation. This is extremely important for what is the next step, so the simulation itself. we need to understand what are the parameters for which we must perform a convergence study, estimate how heavy is the calculation, or if there is any trick for speeding up convergence for large systems, for example. Fourth is the running of the simulation. Before running the simulation that gave us the final result, we must perform a convergence study to choose some of the numerical parameters. This will depend on the approach and on the numerical implementation. If the system is large, we also need to see what is the most effective way, for example, for parallelization, and whether we need to apply any speed up of convergence if this is available. Also, at this point, we input the information on the material, in particular its crystal structure. After this whole process, one gets their output. Is that what one expected? Yes, no? If not, there are many points where it could go wrong. Let's review the process, starting from the last part, the simulation of the numerical approach. Are the numerical parameters well chosen? Is the result well converged with respect to the parameters? Is there any artifacts due to some numerical approximation or approaches? Once we have checked all these questions and found that this is not the case, we turn to the theory. Are the assumptions, approximations justified, and in the case that we are studying? Finally, as well, we just find out that this is all fine. Then, as for the case of the alien race at the start of this lecture, the question that we are posing may be wrong or not precise enough. Simply, we may be calculating the wrong quantity or the wrong material. We need to realize that there is any shortcut than going through all these layers of complexity, and this will just be done through studying the topics that will be highlighted in the lecture of the school. So first we need to study and reading about the phenomenon, about the theoretical approaches, and about the numerical methods. Then we need to put all this knowledge into practice in the hands-on tutorial. During the tutorial, you will learn that given the phenomenon, what are the appropriate approaches, and as well, how do we choose the parameter so that we get an accurate calculation at a reasonable computational cost. Let's consider an example. Suppose we seek to reproduce this experimental result, which is the optical absorption spectrum of lithium fluoride. First, which quantity do we need to compute? In the previous talk, we have seen that the key quantity to calculate is the macroscopic dielectric function. Its imaginary part is the optical absorption. Second, which theoretical approaches are available in Yambo and to calculate the optical absorption? Which one would be the most appropriate? Well, we don't know so much yet. We only have had one lecture, so the previous one, and just refer to that one. In there, within the linear response, the dielectric function was linked to the density-density response function. Further, the latter was obtained for a Kohn-Sham single particle Hamiltonian, where the Kohn-Sham potential was calculated at the zero field electronic density. So this was the independent particle response. further, how is this response calculated in Yambo? Well, we will use plane wave, so we take the Kohn-Sham orbitals and energies from a plane wave density functional code. So we use a plane wave basis. So what before was just indexed with an n, now is indexed with an n and crystal momentum. And then this is the expansion into plane waves. So G is the sum, is the reciprocal lattice vector, so we have an, in principle, infinite sum over reciprocal lattice vector. So then you can substitute in the previous expression the expansion in plane waves, and then if you work out, it will be quite a complex expression, and you will see in the hands-out there is something which is called cheat sheet, which contains all these expressions, so you can refer to that. But what is important, what is also highlighted there, are all the sums which need to be truncated. So in the case of the density response in the independent particle, we need to truncate, for example, the sum over the conduction bands, and then all the integrals over the brilliant zone need to be discretized, and in this case you will use the same K-mesh that you used in your density functional calculation. So if you have to change that, you have to repeat the density functional theory calculation. Finally, we are at the fourth layer of complexity. We must set up the simulations. First, the material. The stable phase of lithium fluoride is a face-center cubic crystal structure, and the lattice parameter is known experimentally or can be calculated using a TFT, for example. We can use a plane waves density functional theory code within the local density approximation or any generalized gradient approximation to calculate the ingredients for the response, so the block functions and the associated energies. Then we converge with respect to the parameters, so we need to determine the K-mesh as we have seen and the number of conduction bands to be included. Finally, this is what one obtains. Clearly, there is a little resemblance with the experimental spectrum, so we need to look back at what we have done. First things to check are the results converged with all numerical parameters. This is essential that you can answer affirmatively, since you need to be sure that the results are numerically accurate. Otherwise, it's impossible to proceed further. So, in this case, the answer is positive. All quantities are well converged. Second, are we calculating the correct property and the correct material? This is important. You need to be sure you are simulating the right experiment, of course. Again, in this case, the answer is positive. And this just leaves out the theoretical approach. Can you list two of the approximations we used to obtain the response function so far? So, the first and most obvious approximation is the independent particle approximation. So we have frozen the density used to calculate the Hartree and exchange and correlation potential to the zero field 1. A second approximation that you may have spotted is that we are using the Bloch function and energies coming from a density function of theory calculation. And you may be aware of that, for example, the band structure obtained with density function of theory is only qualitatively correct, not quantitatively correct. So this may affect the result as well. Further approximation you may have thought about are the linear response. So we are neglecting all nonlinear effects, and we are also working at zero temperature. So finding a better approximation for the latter 2 points goes beyond the scope of the school, which is a school for for beginners. However, we will see improved approximation for the first 2 points. In the previous lecture, besides the independent particle approximation, you also have seen the time-dependent density function of theory and the time-dependent Hartree. A difference with the independent particle, we had that part of the Kohn-Sham potential, in particular the Hartree part and the exchange and correlation part, depends on the time-dependent density. So the variation of the Kohn-Sham potential is equal to the variation of the external potential, that is the initial external perturbation that one applied to the system, and then also to the variation of the Hartree and exchange correlation potential, which is a consequence of the fact that the density is changing, and those quantities are functional of the time-dependent density. Let's take the functional derivative of the Kohn-Sham potential with respect to the electron density, using the fact that the density is the same in the physical system and in the Kohn-Sham system. Then we recognize that on the left-hand side we have the inverse of the Kohn-Sham independent particle response. On the right-hand side, the first term can be recognized to be the response function. The second term is the contribution from the Hartree potential, and the third term is the contribution from the exchange and correlation potential and what is called the exchange and correlation kernel. So finally we can rewrite it to obtain a Dyson-like equation that links the time-dependent density functional theory response, or if we set the exchange and correlation kernel to 0, the time-dependent Hartree response with the independent particle response. In the hands-on tutorial, you will find how this quantity is evaluated numerically, and again, if you will be provided with a so-called cheat sheet where you will also see highlighted what are the quantities that need to be the quantities that need to be converged. So some that needs to be truncated, and integration over the Brillouin zone that need to be discretized. Unfortunately, the results one gets for either the time-dependent Hartree or the time-dependent local density approximation are very similar to the independent particle. The fact that the time-dependent Hartree, also called random phase approximation, and the time-dependent density functional theory with standard exchange and correlation approximations are similar to the independent particle, it's common to periodic semiconductors and periodic system such as semiconductors and insulators. Tomorrow and next week you will learn about the GW and the beta salpeter and see how their combination would produce a good agreement with the experiment. Coming back to 42. If you run Yambo as any other code that is not meant to be used as a black box, if you use Yambo as a black box, you are likely to get many 42s. So finally, to answer the question, how can we make the most out of Yambo? We need to acknowledge that there are several levels of complexity. We need to read over the physics, the theory, the numerical approach, and in this school, this part is covered by the lectures. Finally, we'll have to learn through the hands-on tutorial, and in the hands-on, what you will learn in the lecture is then linked to the input keywords, and you will also learn how to choose their values. That's all. Thank you for listening. Have a great Yambo school and read, learn, run.